In the previous video, we looked at the relationship between the change in free energy, delta G, and the reaction quotient Q. And we plugged in different values for Q, and we saw how that affected our answer for delta G. The sign of delta G told us if a reaction was spontaneous or not. We also said that at equilibrium, Q, the reaction quotient, is equal to the equilibrium constant K, and we plugged K into the equation and solved for delta G. Delta G was equal to 0, so we know at equilibrium the change in free energy is equal to 0, so there's no difference in free energy between the reactants and the products. Let's plug in delta G is equal to 0 into our top equation here, so we have 0 is equal to delta G0, the standard change in free energy, plus R times T, and since we're at equilibrium, delta G is equal to 0, this would be the natural log of the equilibrium constant K. So we solve for delta G0. Delta G0 is equal to negative RT natural log of K. So we have another very important equation to think about. Delta G0 is the standard change in free energy, or the change in free energy under standard conditions. R is the gas constant, T is the temperature in Kelvin, and K is our equilibrium constant. So if you're using this equation, you're at equilibrium. Delta G is equal to 0. And we know at equilibrium, our equilibrium constant tells us something about the equilibrium mixture, right? Do we have more products or do we have more reactants at equilibrium? And this equation relates the equilibrium constant K to delta G0, the standard change in free energy. So delta G0 becomes a guide to the ratio of the amount of products to reactants at equilibrium because it's related to the equilibrium constant K in this equation. If you're trying to find the spontaneity of a reaction, you have to use this equation up here and look at the sign for delta G. So if you're trying to find if a reaction is spontaneous or not, use this equation. If you're trying to find or think about the ratio of the amount of products to reactants at equilibrium, then you want to use this equation down here, and that ratio is related to the standard change in free energy, delta G0. Now we're ready to find some equilibrium constants. Remember, for a specific temperature, you have one equilibrium constant. So we're going to find the equilibrium constant for this reaction at 298 K. So we're trying to synthesize ammonia here. And at 298 Kelvin, or 25 degrees C, the standard change in free energy, delta G0, is equal to negative 33.0 kilojoules for this balanced equation. So let's write down our equation that relates delta G0 to K. Delta G0 is equal to negative RT natural log of K. Delta G0 is negative 33.0 kilojoules. So let's write in here negative 33.0, and let's turn that into joules. So times 10 to the third joules. This is equal to the negative. The gas constant is 8.314 joules over moles times K. So we need to write over here joules over moles of reaction. So for this balanced equation, for this reaction, delta G0 is equal to negative 33.0 kilojoules. So we say kilojoules or joules over moles of reaction, just to make our units work out here. Temperature is in Kelvin, so we have 298 K, so we write 298 K in here. Kelvin would cancel out, and then we have the natural log of K, our equilibrium constant, which is what we are trying to find. So let's get out the calculator, and we'll start with the value for delta G0, which is negative 33.0 times 10 to the third. So we're going to divide that by negative 8.314, and we'd also need to divide by 298. And so we get 13.32. So now we have 13.32, right? So our units cancel out here, and this is equal to the natural log of the equilibrium constant K. So how do we solve for k here? Well, we would take e to both sides. So if we take e to the 13.32 on the left and e to the natural log of k on the right, this would cancel out, and k would be equal to e to the 13.32. So let's do that. So let's take e to the 13.32, and that's equal to, this would be 6.1 times 10 to the 1, 2, 3, 4, 5. So 6.1 times 10 to the 5th. And since we're dealing with gases, if you wanted to put in a Kp here, you could. So now we have an equilibrium constant K, which is much greater than 1. And we got this value from a negative value for delta G0. So let's go back up to here, and we see that delta G0, right, is negative. So when delta G0 is less than 0, so when delta G0 is negative, what do we get for our equilibrium constant? We get that our equilibrium constant K is much greater than 1. So what does this tell us about our equilibrium mixture? This tells us that at equilibrium, the products are favored over the reactants. So the equilibrium mixture contains more products than reactants. And we figured that out by using our value for delta G0. Let's do the same problem again, but let's say that our reaction is at a different temperature. So now our reaction is at 464 Kelvin. So we're still trying to make ammonia here, and our goal is to find the equilibrium constant at this temperature. At 464 Kelvin, the standard change in free energy, delta G0, is equal to 0. So we write down our equation. Delta G0 is equal to negative RT natural log of the equilibrium constant K. And this time for delta G0, we're plugging in 0. So 0 is equal to, we know that R is the gas constant, and we know that the temperature here would be 464 Kelvin. So for everything on the right to be equal to 0, the natural log of K must be equal to 0. So we have 0 is equal to the natural log of K. And now we're solving for K. We're finding the equilibrium constant. So we take e to both sides. So e to the 0 is equal to e to the natural log of K. E to the natural log of K is just equal to K. So K is equal to e to the 0, and e to the 0 is equal to 1. So when delta G0 is equal to 0, so let's write this down here. So when your standard change in free energy, delta G0 is equal to 0, K is equal to 1. And that means that at equilibrium, your products and your reactants are equally favored. Let's do one more example. So let's find the equilibrium constant again at another temperature. So now we're at 1000 K, and our standard change in free energy, delta G0, is equal to positive 106.5 kilojoules. So delta G0 is equal to negative RT natural log of K. This time we're putting in positive 106.5 kilojoules, which is positive 106.5 times 10 to the 3rd joules, is equal to negative, R is our gas constant, 8.314. I'll leave units out of this just to make it a little bit clearer, times the temperature, which is 1000 K, so this would be 1000 Kelvin, times the natural log of the equilibrium constant K. So let's do the math there. We'll start with our delta G0, which is 106.5 times 10 to the 3rd. So we're going to take that value and divide it by negative 8.314. And then we need to divide by 1000, and that gives us negative 12.81. So we have negative 12.81 is equal to the natural log of the equilibrium constant. So to solve for the equilibrium constant, we take e to both sides, and we get that K is equal to e to the negative 12.81. So what is that equal to? E to the negative 12.81 0.81 is equal to 2.7 times 10 to the negative 6. So K, the equilibrium constant, is equal to 2.7 times 10 to the negative 6. So when delta G0 is positive, when the standard change in free energy is positive, let's write this one down. So when delta G0 is greater than 0, so when it's positive, your equilibrium constant K is less than 1, right? So K is less than 1. And we know what that means at equilibrium. The reactants are favored at equilibrium. So your equilibrium mixture contains more reactants than products.